Welcome to Mechanics of Composite Materials. Today I'll be covering the motivation, the course overview, and application of the concepts that we'll be talking about. And my name is Vinay Goyal. I have a bachelor's degree in the mechanical engineering from the University of Puerto Rico, Mayagüez. I have a PhD in aerospace and ocean engineering from Virginia Tech. And I have an extensive background in structural systems, including aerospace structures, composites, bolted joints, bonded joints, dynamics, and failure modes. And the failure modes I've been involved in are failure modes related to composites, fracture mechanics, fatigue, buckling, and so forth. I have extensive experience in the area of systems engineering, reusable launch vehicles, and spacecraft applications. I really enjoy basketball, chess, hiking, beach, and I'm a foodie. You can email me anytime at this email address. In addition to that, I'm involved with several NASA activities, and also work with the government on a lot of different projects. I have a vast familiarity of the use of composites in several arenas, including aircraft, launch vehicles, commercial applications, spacecraft, and other systems that may be used, even things such as a golf club, as an example. What is the motivation? The motivation is that advanced composite materials are extensively used in high performance applications. And so they can be used in automotive to decrease weight in aircraft and ship systems, and including launch vehicles and also spacecraft. And the reason we use composite structures is because by decreasing the weight of the systems, we're then able to increase the efficiency and performance of these systems. So I can use less fuel if an aircraft uses composite materials as an example. So this course is intended to provide a background on the theoretical and practical foundation of composites. The topics in this course are fundamental to the analysis, manufacturing, and design of vehicle and civil structural components. And what are the objectives of this course? In this semester and in this course, what I plan for us to do is to really gain an understanding of the fundamental concepts in the analysis and design of laminated composite materials. And to do that, what we want to do is to understand the various methods for the manufacturing processes of composites. We're also going to cover experimental methods for the characterization of composite materials. I think that's a very important arena that's usually not looked at carefully, but impacts significantly the systems that we work on, because the experimental methods you use can drive the strength used in the analysis of a lot of the systems. Design and analysis of composite materials, we'll be covering that, and how to tailor the composites to get the best performance. We'll then cover the failure criteria that exist to predict the failure of composite materials, and then we'll then talk about the design considerations that you need to keep in mind as you apply them in real systems. And I hope all these ideas come to fruition through this course outline as we go through it. What I'd like you to do is to not only study the materials I'll be teaching, but I also want you to focus on materials outside of the materials I'll be teaching here, because I think you will learn a lot. One of the things I want you to do is to enroll in Composites magazines, and you'll see that in some of the work you'll be performing. But the idea there is to get exposed to a lot of different ideas that and get informed about how composites have evolved, how these materials have evolved, and what are some of the new applications these are being used in. So in today's lecture, we're covering the motivation. We'll be moving to material science, manufacturing, and micromechanics, and applications as well. And then from there, I'll give a very top level view of solid mechanics. The idea of solid mechanics is covered much extensively in a different course. So here, what I'll do is provide a very top level view of that. And then we'll cover the characterization of material properties, which is, like I said before, is extremely important for us to look at that carefully. What kinds of testing I need to really get the material properties for the system of interest. Then I'll be talking about approaches to determine equivalent material properties. And when we get there, you'll better understand what that means. But then later I'll move to the analysis of laminated composites. And that's really the mechanics of laminated composites. You'll be learning some of that material as well. And from there, I'll move to optimization, tailoring, and the idea of energy methods, which is quite mathematically intensive. But the idea of this topic is to teach you that that forms the foundations for finite elements. And this topic tends to be a graduate level course, and so that's okay. I'm not going to make you really rederive these equations. It's really to show you where things come from. Then we'll move to sandwich structures, and then to failure theories, and then to design considerations. So composite applications, they're used in extensive number of applications, including a turbine blade that you see here, and they typically fail in fatigue in these applications. Composites are also used extensively in aircraft design. And the 787 body, which is made by using a lot of composites, over 50%, in the main fuselage body, the metallic gray, with a combination of aluminum, which is the red, 20%, titanium, which is orange to some percentage, which is fairly low, and then steel at 10%, which is blue and shown here, and then other materials. The composites really have increased the performance of a lot of systems. And this is very, very good, and that's why it's being used. But they have also significant amount of downsides. They have upsides and downsides. By comparison, if I were to compare this aircraft to a 777 used 12% composites and 50% aluminum. So the 787 is a much more advanced system, it's more robust, but also provides higher performance compared to heritage systems. So, what are composite materials? And the composite materials is really the combination of two or more materials. And the types of materials we'll be discussing here is a matrix. You're going to have a matrix material with a fiber impregnated within the matrix. The matrix material tends to be such that's malleable. So, before you cure it, it's malleable. And that material, that matrix material, is soft at the beginning. It holds the fiber and binds the fiber together. That's the whole point of the matrix, is to keep everything together. I'll look at it similar to, say, a shirt. You can see the fibers running through your shirt, perpendicular directions. But think of that shirt now bath on a glue some sort, a resin glue of some sort. So that's what we're talking about. That resin material, when it hardens, now it's going to have the fibers impregnated in that material, running perpendicular to each other. And so now when that glue hardens, now you're going to have a composite material that's quite strong because the material now is going to have those fibers going through. If you heard of wood structures, the wood structure is basically composite materials because you have these fibers going through the trunk of that tree or the wood, and that fiber is really providing that strength. Another application of composites that you may have heard is reinforced concrete. Concrete, you can have concrete with steel bars going through them. Well, there the steel becomes your fiber, and the concrete is your matrix. Matrix is going to be the one that holds those steel bars together. And the matrix in that case is providing the load transfer from fiber to fiber. If that matrix was not there, then each fiber acts independently. The matrix usually is ductile, it's a tough material, and is low density. And the strength usually is way lower than fiber, similar to reinforced concrete. The concrete is very low strength, but the fibers are high strength. The reinforcement in that scenario. The matrix also serves a very important aspect. The aspect there is that the matrix provides shape to the structure. And that's extremely important in what is done. Because if I have a curved structure, just by me having fibers, that's not going to cut it. I need to have shape to that structure. And to give it shape, the matrix can help me with that. Fiber is a reinforced material, it's a reinforcing material, and is also known as a filler. It carries about 75% to 90% of the load, while the matrix carries a much lower percentage. I'll explain later why that is. The fiber provides structural properties to the composite, such as stiffness and strength, and it provides thermal stability and electrical conductivity or insulation. It can actually be very good at that. So, in reality, at the end of the day, bottom line is we're going to study materials where the fiber is embedded within the matrix. And here I have a pictorial of that. Here you can see the matrix material. Clearly, it's not going to look like this exactly. In reality, you're going to have a fiber bundle or tow of fibers in the 12K range, 12,000 fibers bundled in a tow. And so that's going to be embedded in the matrix. You're going to have a lot of these fibers running along the length of that composite. And I'll teach about the types of composites we can have later. You have the lamina. So at the lamina level, this is going to look like this. You're going to have a laminated composite. A lamina, single lamina is going to look like this with fibers running along one direction. That's one potential option. You can have other options where the fibers run perpendicular in two directions and they're perpendicular to each other. You have composites where the fibers run in three directions. We call those traction braided composites. I'll be teaching that a little bit later on. But the kinds of composites we're talking about are laminated composites, where I take multiple laminas, and you can see here, this lamina here is running at a particular angle. This lamina here is running at a different angle. Each lamina could be tailored to give you the optimal performance for the actual application. So when you use that in the actual structure, you're getting the best performance you can. And that's the whole point of composites. If I were to use aluminum and every direction had the same properties, then obviously I have less knobs to turn in order to optimize a structure. For aluminum, if I were to give in a material like aluminum, the only thing I can really do is modify the thickness. And maybe I can change the material, but I don't have a lot of options, right? Just one option there. So again, what I'm trying to say here is that with composite materials, I can change the ply angles. So these angles can be changed. These ply angles can be changed. I can change the fiber system. I can change the resin system. So I can even change the thickness to some level. I can actually tell you how many plies I want even. Not only can change the angle and the number of plies, I have knobs I can turn. I can change the angles. I can change the thickness. I can change the material of the resin. I can change the material of the fibers. If I have a metallic structure or metallic part, I cannot change the ply angles because I'll get the same properties. Doesn't matter which angle I put the metal in, I'm going to get basically the same behavior. So that's what we're trying to say with knobs to turn. I have more possibilities with composites than I do with metal. I have more options. Now with additive manufacturing, there's now the ability to do more even. But that doesn't mean that we have even that number of knob to turns because now with composites, now there's also 3D printing as well. Okay. So that's what we're talking about here. Okay, so there are a lot of different types of composites. So you can have a particulate composite. Concrete to me is particulate composite because if you put stones, rocks, and sand and the binding material, that's basically a particulate composite. But we're not going to cover this kind of composites. You could have a situation where you have fibers running randomly within a block. We call that fiber reinforced composite. We're also not talking about this one. You could have flake composite where the fibers are chopped and maybe they have a very non-uniform fiber distribution across the composite. We're not covering that either. Now, you can apply the ideas of this class to these types of composites. Very easily to do. Very easy to do. But the kinds of composites we'll be covering in this course is laminated composites, which are going to look like this. It's going to look orderly. The fibers are continuous, and they're laminated. So I can stack the composites like this, and this is what is used for 99% of the applications. You could have these other ones, but the ideas I'm teaching in this course can still apply to these other ones. It's just I'm going to specialize what we teach to this class of composites. Okay, so that's what we're talking about here. We're not saying we're not going to cover the other kinds of composites, but that we're emphasizing the idea of composite materials in light of laminated composites. That's what we're talking about. I'm going to go ahead and share a video of composites. So as you saw, we were looking at the manufacturing of a composite, and the manufacturing of a composite can be such that a lot of different defects could occur, and that includes porosity, defects between plies, indentations from the pressure sensor, and many other things that we'll be covering later. And the reason I was showing that slide, those videos, is so you can get familiar with how the composite looks like. You're not able to touch it, but you can see the texture from afar in that video. And you can see kind of like the very top level view on how it's made. And so why we need to learn composites is because composites can be tailored to get the most out of a design. That's really the bottom line. Now, if you use composites and you use the standard set of angles, say you use 0 plus minus 45 90 symmetric. And when I say 0 plus minus 45 90 symmetric, what I mean is that the laminate, the fibers are running along the 0 degree direction relative to some global direction that you define. The 45 degree, the laminate, the lamina that follows us on top is going to be at a 45-degree orientation. And then the minus 45 is going to be in the minus 45-degree orientation relative to the global coordinate system. And then finally, I'm going to add a 90-degree ply on top, which will be perpendicular to the very first one you put, which was 0-degree ply. So the 90-degree orientation means that the plies are running, the fibers are running along the 90-degree orientation relative to the global fixed direction that we define. And I said symmetric because the ply that follows will be 90 minus 45, 40, and 0 degrees. So you'll have 8 plies. That ply stacking sequence I just talked about is a very commonly used stack uh, ply stacking sequence. And that ply stacking sequence may not be the best for every design. So just because you use composites and it sounds cool, and you tap into the 0 plus minus 45 90 symmetric, doesn't mean that you got the best out of the composites. Because if you have more loading condition in in a particular direction, I want more fibers oriented along the loading direction that's primarily say at 0 degrees. So if the loading condition is primarily at 0 degrees, I want to have as many plies as I can along that direction because I want the fibers to take the load. So it's very important to understand that to tailor composites, I just don't go to the standard 0 plus minus 45 90, which I see in a lot of designs. I see a lot of designs just go to the 0 plus minus 45 90 symmetric, but you're not gaining a lot by using that ply stacking sequence. It could be correct for some applications, but it may not be the best for if the loading conditions differ from direction to direction, from one to direction to another. Composites, while they sound cool, and while you can decrease weight, and while they offer a lot of advantages, they may not always be the best choice. It depends on a lot of different factors, and you have to consider it. Say if I'm going to make one or two products and I don't plan to use it for a long time, maybe composites make sense there if I really need the performance for those two products. But say I want to use composites for a very long time and I don't really need the performance, then maybe composites is not the best choice because composites offer have a lot of issues during manufacturing, and there's overhead associated with their use. They're expensive, and they're expensive to maintain, and they're expensive to inspect, and they can come with issues. So you have to really balance whenever you need composites, and whenever you want to use composites, you want to really investigate whether that's really something you want to do. There's also cost associated with that, their schedule, and so as a consequence, you want to look at the trades and determine is that the right thing for me to do because it may not be the right thing to do. Every situation is different. And so you have to really determine through a cost trade study, a scheduled trade study, and understanding the infrastructure that you may need to make these composites. Because you're also going to need infrastructure. You're going to need an autoclave potentially. You're going to have to need non-destructive evaluation procedures to look at the production that you had. You have to consider a lot of factors, and as a consequence, it's of extreme importance that you look at all these factors together. Analysis alone is not sufficient for the certification of composite systems. You have uncertainty in failure modes, complexities of failure modes. You have variability in manufacturing, workmanship issues, and process dependent issues. And as a consequence, and I bring up these three topics that may be disjointed to you right now, but these are the three challenges that we face with composites. We want to use them, but you have to get the best out of them. You can't just use them because you want to. The second thing is decision making. Should I use them or not? But I have to really evaluate the life of the program, the schedule, the cost, and do those trades to understand whether it's really advantageous for making profit, which could be the end goal for your organization. And then the third challenge is that you can analyze metals very easily. But when it comes to composites, it's not that easy. And you do require a lot of testing, a lot of understanding of how the material behaves, a lot of understanding of the failure modes, a lot of understanding of the workmanship issues that you could encounter, the understanding that each build is going to look different from the next build because there's variability when it comes to composites. Understanding that even a small change in the process on how to make composites can affect the strength. And I already showed you a video that shows all the steps that it takes to make them. Even if there's a vacuum leak or a small imprint, or if the person did not use gloves and the grease was touching, or if they're using gloves but they're contaminated, or there's sealing paint that fell down onto the composite. All those things need to be looked at because it's going to affect the strength of the composite. Analysis alone is just not sufficient. And the fact of the matter is that these five components that I'm talking about have a direct impact on the cost and schedule. So you have to really balance, is composites really the right thing to do for this application? I don't want to just use composites because they sound cool. I want to use them because it's necessary for the application of interest. And that's what you want to really try to strive for, to do the right decisions for the right application. And so now what I want to do is I want to move into an application. So let's look at an actual application. And here what we're going to look at is a composite ramp. It's a foam core sandwich structure, which is subjected to thermomechanical loading. And the reason I'm presenting this example is to demonstrate an actual application and the challenges that you can have with composites. Here, what I'm going to cover is the motivation and objective of the study, material and test selection, fabrication, non-destructive evaluation, testing, and then I'll cover the finite element analysis. And then I'll then conclude with some thoughts. So what is the motivation? Motivation of sandwich structures is they're really used for primary aerospace structures. And sandwich structures do help with decreasing weight because when you have a sandwich structure and you put something lighter in weight, so this is a sandwich structure here as an example. If this is lighter weight than the composite away from the core, say the core is very, very light, like foam, and then this is a very strong composite in dark green, then this is going to be very light compared to if everything was composite, right? Like on the left side. And so in a lot of applications, you may use very strong and you may use a lot of composite um, laminates, like this one here, in areas where you need it. And you may use sandwich structures in whatever you need it to. But in a lot of applications, you may need to use both. And so sometimes what they do is you will taper, you will transition from only laminate, you will transition to something where there's core in between The face sheets, I call these gray portions face sheets, or these are the abutments. So basically, these gray here are composite, laminated composites, just like this one, but now that's going on top as a foam, basically on top and bottom of the foam core. And the idea there is that this will provide great bending stiffness and it will decrease the stress due to bending loading. And that's the whole point of a sandwich structure. It's really good for stability. It's really good for decreasing the stresses in the face sheets. And while a laminate could be good too, you may need both. And so this is where a transition could be incorporated into the design. And so the idea here is that you need to understand the strength capability of sandwich core composites and understand how, in this application, what was needed to be understood is how this foam sandwich structure could behave due to being loaded by mechanical loading and also by thermal loading. Both of those conditions needed to be considered. And so, as a consequence, we need to then determine, because these are used quite a bit in aircraft and launch vehicle designs, we need to then determine how to predict those failures accurately. And here you have a lot of failure modes that could be considered. For example, the foam could crack, or if it's a deep, there's a debond, some sort of the separation here due to bad workmanship that could grow, or you could have delamination, this between the laminates to delaminate. For example, it could come apart here, and fiber failure as an example, or tension failure of this foam. So you can have a lot of different failure modes, and so you have to consider all of those in the design process. Okay. So what is the idea? The objective is to determine the tensile strength reduction for as designed asymmetrical taper foam core sandwich structure at low temperatures. And so the idea is then determine when the structure will fail due to this loading condition. And so the idea is to predict the tensile strength for different asymmetric taper designs at operational temperatures using a verified approach. So the problem is that not every design is going to look the same. That's the bottom line. You may try to test some stuff in the labs. You may try to analyze it, but that is only good to that design. And so the idea is to develop an analysis tool. Anytime I talk about analysis, right? I say analysis is not sufficient. Anytime I talk about that, analysis also helps you to gain confidence. So say your analysis matches the testing very well, then you can use analysis as a transfer function and look at other designs as long as the failure modes are consistent. And so if I'm able to come up with an analysis approach that's able to verify this design, perhaps I can use that analysis to look at other designs. So that'll be very valuable, right? That'll be a good objective. And here I'm providing the kinds of materials this was made of, so you're aware of it. You have a film adhesive 181. So a film adhesive, uh, for example, will be a very thin layer that glues everything together. IM7 is a type of fiber, while 8552 is the type of epoxy. So that's a laminated composite. The fiber and the resin are this formulation here. And these two together is what makes up the lamina. Of course, we have multiple ply angles, so that needs to be considered as well. 200WF happens to be the Rohacell foam core used in this application. So that's a foam here in green. In-house material level testing needs to be completed to understand the full strength capability of the Rohacell foam, of the composites, and the film adhesive. You want to get a good understanding of all these components. Now you can see right there the difference between composites and metal. If I had a metal and I didn't have to do any of this, I didn't use any of these materials, I just characterized the aluminum. That's all I do. In this case, I have to really look at everything, including how these materials interact with each other. You have to. The test coupon needs to be designed also to ensure that you get the failure mode of concern. So if foam is your failure mode of concern, you want to make sure your test can give you data to look at that at the coupon level, uh, right? And so we also need to load this up because in actual application, this is loaded, including the exposure to cold temperatures. And so you want to make sure you have both. And so this in-plane testing machine included the instrument machine to apply the loading condition. And then you have environmental chamber, which is where you put the composite, you condition it to the humidity and temperature you want it to then test it. That's the goal there. You can see here the spacing fabrication. The foam blanks were cut from with using a CNC machine, and then the plies were hand laid up, just like we saw in the videos. You put the layers on top of each other, and then you bring it to a mega or very big autoclave to cure it, to cure the material, so that the resin that was soft becomes hard. The sample coupon fabricating is fabricating to verify also the manufacturing process. You want to check that out. You can see here that the zoomed in version of this, but you can see it looks quite smooth and quite good. It's a good fabrication process there. And then you want to perform a non-destructive evaluation. I'll touch on that later. X-ray, ultrasound, and the idea there is when you send a sound signal through it, if there's a delamination somewhere in between where two plies are separated, then the sound will bounce off from the free surface and shoot back up. And that's how you know there's an issue between plies. That's one approach. Uh, the second approach is to perform X-ray. That's one approach, and that'll produce an image, but not always is going to be perceptive to delaminations like I talked about. And here you see colors, and the colors are just representative of what's going on with the bond line, what's going on with the composite ramp design. Because this is a ramp here, it goes up, becomes thick, and then a ramp again here. So I'm not covering the exactness of what this defect is, but bottom line is it was going to be cut here anyway. It's going to be cut right there. So that doesn't play a big role.
For like the
So the design of the test, you can see here the foam core in white. You can see the black is a composite that's laminated. You can see here very thick laminated composite. And so this transition helps you go from laminated composites to a design where you have a sandwich structure. And it's very
yeah.
beneficial, like I said before. You're using the materials where you need them the most, and you're using other materials where you may need them less.
So my question was
Both the
primarily
connections
on
at the
the
top and bottom
oh,
test fixtures. So you can see here, there's fixtures here and here and here and here. Those test fixtures provide boundary conditions that are they're basically clamped, and so they're good for what we're doing. The instrument tensile testing machine then is tested. We test the samples at temperature, at hot temperature, cold temperature, and room temperature. Because in this application, we're interested in cold temperature. You can see here that we have a video system to capture any failures really quickly. That's very important when you do testing with composites, is to have good equipment to track the any initiation of cracks and really trying to understand if we're missing something big. The tensile test program encompassed 70 degrees, minus 26 degrees, minus 58 degrees, and it was within the flight experience. That was the whole point of doing this test battery. 3 coupons were tested per configuration, and usually you want to also involve the idea of moisture that should be looked at. And so encourage you to look at that as well. Um, you also have tensile testing at room temperature performed in open air, and then tensile testing at cold temperature performed with a controlled environmental chamber. Here's the results. You can see here that you apply the tensile load and the cross-head deflections. And you can see a failure there. The load dropped quite significantly. You can see a crack forming here. And the test results are provided here. We have several tests per samples. And you can see here, these are the 3 for 70, 3 for 27, and 3 for 57. And you can use that now to then study why this could have occurred. Why, you can see here very quickly that At cold temperatures, the strength, the loading applied to this coupon is really low compared to the room temperature one. So something was going on really that needed to be understood, because in the actual application, the failure load is actually way smaller than if you were tested at room temperature, which is not intuitive. You'll expect that the test configuration somehow will be the critical condition, and it is in this case, but it doesn't encompass all the other conditions, room temperature and so forth. And so, as a consequence, it's important to instrument the samples really well, so when failure occurs, you can pick it up and then assess it. Here you can see a high-speed video. I think it's important to invest on that. The high-speed video from the room temperature test is provided. Here you can see how the cracks kind of initiate there. I'll let you look at it for a couple of minutes, a couple of seconds. So once I have that, you can see the crack initiates and propagates a little bit. And this is 38 microseconds intervals. You can see the crack is propagating really fast across the sample. So why is high speed video useful? So when I look at this figure, it's very unclear where the crack initiated. So when you're designing something, it's very important to know where it initiated, because that's your limit in the design. If I went by this picture, it's unclear where it started. So the high-speed video clearly shows it started within the foam, which was unexpected. Nobody expected it based on this picture. But look at this picture clearly. The crack initiated with the foam and had to be addressed in future designs. And so that's what is done typically now. Here's a high-speed video for cold temperature test. You can see here quickly how the crack grows relatively really fast, and it shows foam failure in the test group from left to right. Um, and you can see here that's for minus 26 degrees F, minus 27 degrees F, minus 57 degrees F, and minus 58 degrees F. So there's a difference in behavior, and you can see that shown by this picture. You can then perform a finite element analysis, and I don't want to go into this in extensive detail, but you create a 3D finite element model with high mesh densities in areas that would matter. We know it cracked here, so mesh it really well there. You want to include the flat face sheet, the ramp face sheet, the interior laminate, foam core, and test fixtures. You want to model all of that if you can, and use surface to surface approaches to tie different surfaces. That can be very useful in the modeling. Geometric nonlinearity is important to include, and fixed boundary conditions at the base were applied, representing the movement of the save of basically leveraging. Yeah, you want to leverage all the information from the test to build these models. Finite element analysis can then be performed step one, step two, step three. So the first step is to bring the sandwich composite core to the stress-free temperature, because initially when you bake something, you bake a composite. The composite is going to be relatively soft. The resin has not hardened. So that's really your stress-free temperature. When you put it in the oven and you heat it up to 300 degrees F, say, then the resin hardens. And so that's going to have some built-in amount of composite residual strength. The one thing I want to mention is that this residual strength can be hard to characterize sometimes. And so in this case, it had to be done because there's failures happening at low levels of loads are way lower by half compared to stuff at room temperature. And that was unclear what was going on. But when you look at more carefully, you can learn about what's going on through this process. The first thing I want to mention is that there is a stress that's developed from cure to a later point in time. Okay. Then step two, you apply the thermal environments from the cold temperature, the room temperature 70 degrees, to the steady state tensile test temperature. So if this composite sandwich structure is going to be room temperature and it's going to really see minus 30, you want to bring it up to minus 30 as soon as possible. We address that in our standards as well, but I think it's important to highlight. You can apply a tensile load until the foam tensile failure occurs. So, three things loaded. First, acute stresses due to temperature contraction or expansion, because you can have both. But in our case, it's going to be contraction. Then you have environmental thermal stresses, and then the loading configuration that came from flight. If you look at the finite element analysis of this, it's actually quite eerie because you can see that we plotted the max principal stress within the foam. And you can see here the values are relatively small, 1,400. But that's important for you to note because very often we think that the only failure mode that could occur is composites, but the phase shift could also fail. And so there is this temptation of not doing anything about it on the foam side, but you have to really pay attention to it because in this case it's critical failure mode. Point being is that if you look at the max principal stress, these arrows from finite element analysis actually match really well with the orientation of the testing that Falcon 9 have uh, performed. So, or anybody can have performed. It doesn't have to be a particular uh, provider. It could be a Boeing or it could be a Airbus. So you have to look at all the loading conditions in general. Here you can see how the finite element analysis matches the strength prediction. And you can see here how the failure load matches really well from analysis to test really well all across. And you may ask why there's so much dispersion here. There's a lot of dispersion there because the failure mode here at room temperature was quite different from the one at cold temperatures. At cold temperature was foam failure, but when you go to higher temperatures, the failure was an interlaminar failure, a delamination failure between plies. And so you want to really look at uh, the whole spectrum. The analysis anchored at this point may not have been as good as predicting failure here. So you have to make sure the failure analysis models work well across the whole temperature range. That's very important before you can start translating these models for other applications. But once the physics of the problem were well understood, it was much easier then to start predicting what could happen here. And again, you can see how this max principal stress is aligned with the and is perpendicular to these cracks that develop within the foam, which tells you that the max principal stress is a good predictor of failure. The conclusion is that when you use systems that are complicated, like the one I showed, a composite ramp, you have to really consider full test, non destructive evaluation, and analysis method to investigate why failure occurred and how you can increase its strength if possible. And we also showed how by looking at the different failure modes of, in this case, we knew or we found through a lot of research that foam failure was happening. But you can see how high-speed video can help you narrow down the failure mode to one, and you can then examine that one in your final model and gain more confidence in the modeling techniques. So it's important to then gain that analysis and testing correlation because then you can use analysis for other things. Tensile failure loads were decreased due to the applied cold temperature, and that's driven by the coefficient of thermal expansion. The composite does not expand much as aluminum, for example. So you have to consider for that extra loading condition. And so what was very helpful was to divide the loading conditions as a function of time. So during manufacturing, we look at that. During uh, temperature conditioning, we look at that. And when load is applied, we look at that. And so by adding all these things together, we can get a grander picture of what could be happening with this composite ramp in this example. And so that basically concludes this particular presentation. So I hope you can now listen to it again and gain an understanding what composites are and look at the videos more carefully and understand what we're trying to accomplish when we talk about composite structures. Okay. Thank you very much for watching.